Dear students, welcome to the EPG Pathshala. I am Dr. Gurmeet Singh, working as a professor of chemistry in University of Delhi. Today we are going to discuss about the module Electron Spectroscopy for Chemical Analysis, abbreviated as ESCA or ESCA, and we shall be dealing with the instrumentation part in this module, which obviously comes under the paper of Surface Analytical Techniques Part 1. When you complete this module, you should be able to understand the introduction of this, the instrumentation involved, and the sources used for this study. Well, when we talk about introduction, X-ray photoelectron spectroscopy, XPS, also known as electron spectroscopy for chemical analysis, ESCA, is the most widely used surface analytical technique. XPS and ESCA are both one and the same thing. Now, this is used very widely because it can be applied to a broad range of materials and provides valuable quantitative and chemical state formation from the surface of the material being studied. The average depth of analysis for an XPS measurement is approximately 5 nanometers. The core technology of the Versa Probe Third is PHI patented monochromatic micro-focused scanning X-ray source, which provides excellent large area and superior micro area spectroscopic performance. Spectroscopy, depth profiling, and imaging can all be performed over the full range of X-ray beam sizes, including the minimum X-ray beam size of less than 10 microamperes. Spatial distribution information can be obtained by scanning the micro-focused X-ray beam across the sample surface. Depth distribution information can be obtained by combining XPS measurements with ion milling or sputtering, as we put it, to characterize thin film structures. The information XPS provides about surface layers or thin film structures is important for many industrial and research applications where surface or thin film composition plays a crucial role in performance, including nanomaterials, photovoltaics, catalysis, corrosion, adhesion, electronic devices and packaging, magnetic media, display technology, surface treatment, and thin film coatings used for numerical applications. When you look at the instrumentation, it's a typical XPS spectrum where it is a plot of number of electrons detected versus the binding energy of the electrons detected. Each element produces a characteristic set of XPS peaks. These characteristic spectral peaks correspond to the electron configuration of the electrons within the atom, that is, for example, it could be 1s, 2s, 2p, 3s, etc. The long path length for detection requires such low pressures. Since hydrogen is not detected, these atomic percentage exclude the hydrogens because it is not detectable under this. To count the number of electrons during the acquisition of a spectrum with a minimum of error, XPS detectors must be operated under ultra-high vacuum. And because electron counting detectors in XPS instruments are typically 1 meter away from the material irradiated with X-ray.
Electron spectroscopy for chemical analysis. Electron spectroscopy for chemical analysis, also called X-ray photoelectron spectroscopy (XPS), is a surface analysis technique that provides composition and chemical bonding information on the surface of the sample. ESCA can detect all elements except hydrogen and helium. The elemental detection limit is typically in the vicinity of 0.5 atomic percent. ESCA can also frequently determine the chemical state of elements, including the nature of chemical bonding. The technique can be used on both conductive and insulating samples, so it has a wide application in both organic and inorganic systems. How it works? In electron spectroscopy for chemical analysis, we use an X-ray beam to bombard the surface of samples so we can measure the core electrons emitted. We have multiple types of excitation source, a non-monochromatic aluminum and manganese X-ray and a monochromatic aluminum X-ray source. The choice of source is based on the sample under analysis. What information is needed about the sample? The X-rays beam penetrates several microns into the sample. When this occurs, core electrons from the atom of the samples are freed, but only the electrons from the near surface region can leave the surface. The instrument collects and measure the kinetic energy of these electrons, from which we can conclude the binding energy which originally held the electron to its source atom. From the binding energy we can determine which element the electron came from, determine the oxidation state of that atom. An argon ion sputter gun can be used to remove the surface layer of the sample and monitor changes in elemental composition relative to depth. Since the escape depth for low energy electron is only 1 to 10 nanometer, ESCA is very surface sensitive. We also perform small spot ESCA, which refers to the ability of the electron analyzer to aperture down to an area as small as 75 micron in diameter. When we combine this feature with a high strength but small X-ray source, we are able to provide a chemical analysis of features smaller than 100 microns in width. Principle of operation: electron spectroscopy for chemical analysis uses a probe beam of X-rays of a single energy. Since it is difficult to focus X-rays, the beam diameter is typically 5 to 10 millimeter for traditional X-ray source and 0.5 to 3 mm for monochromatic X-ray source. The X-rays penetrate several micrometers into the sample at typical ESCA source energy, liberating electrons from the atom of the sample. The kinetic energy of the liberated electron is the known energy of the X-ray photon minus the binding energy of the electron in the atom. Measuring the kinetic energy of the electron as it is collected, therefore allow the binding energy to be computed. The binding energy tells us not only what element the electron come from, but also what chemical state the atom was in. Since the escape depth for low energy electrons in is 1 to 10 nanometer, ESCA is very surface sensitive, as in SAM. An argon ion sputter gun can be used to remove surface layer and to monitor changes in composition as a function of depth. Small spot ESCA derives its name from the ability of its electron analyzer to aperture down the area seen on the sample to an area as small as 75 microns diameter. This feature, coupled with a high strength, relatively small beam X-ray source, provide the capability to extend chemical analysis to features smaller than 100 micron wide. Basic physics: a typical XPS spectrum is a plot of the number of electrons detected versus the binding energy of the electron detected. Each element produces a characteristic set of XPS peaks at characteristic binding energy value that directly identify each element that exists in or on the surface of the material being analyzed. These characteristic spectral peak correspond to the electron configuration of the electron within the atoms. Example 1s, 2s, 2p, 3s, etc. The number of detected electrons in each of the characteristics peak is directly related to the amount of the element within the XPS sampling volume. To generate atomic percentage value, each raw XPS signal must be corrected by dividing its signal intensity, number of electrons detected, by a relative sensitivity factor called RSF and normalized over all of the elements detected. Since hydrogen is not detected, these atomic percentages exclude hydrogen to count the number of electrons during the acquisition of a spectrum with a minimum of error. XPS detector must be operated under ultra high vacuum UHV condition because electron counting detector in XPS instrument are typically 1 meter away from the material irradiated with X-rays. This long path length for detection requires such low pressure.
Now, coming to the instrumentation, there are many components. The major components of this instrument are electron energy analyzer, 100 millimeter radius it has, concentric hemispherical analyzer, we call it, and voltages vary from one to another to pass energy. Then we have X-ray source, argon ion gun, neutralizer, vacuum system, electronic controls, detection of elements, electron multiplier. This is called Chenetron also. Avoid surface reactions and contaminations. It avoids surface reactions and contaminations when we use this last part in this. The most important in this first part is electron energy analyzer, because this is the one which sends varying amounts of voltages to the target. So it varies from low energy to high energy, and gradually we can change this also. A flow chart of this spectrometer. It has various units as it is indicated in this slide. Spectrometer control unit is the major one. Then we have the voltage passing side where high voltage is passed, and then through series of intermediate voltages, the other side of it indicates low voltage, or as we call it, hemispherical sector analyzer. Similarly, we have channel electron multiplier, electrostatic transfer lens, then analyzer entrance and exit slit plate, amplifier, then reflectometer, and finally we come down to the graph, which is on XY recorder, it is plotted. This is how it looks like, that has been shown in this slide. Electron spectroscopy, the principles once again, to recapitulate: sample ionized by a radiation and it emits electrons which are observed. Then we call it photoelectron spectroscopy also. The other name obviously is electron spectroscopy for chemical analysis, as we call it, ESCA, ESCA. The B part deals with UV photoelectron spectroscopy. This is another name given to this. Second side of this is Auger electron spectroscopy, because in one of the analysis that we get through this, the electron that is generated in the vacancy which is created is called Auger electron, and this is called Auger electron spectroscopy, which is similar to this. Then we have another similar kind of spectroscopy, which is electron energy loss spectroscopy, EELS. So if we sum up, electron spectroscopies are of three different kinds, and in all these what we find is it is the sample that is ionized by a radiation and the emitted electrons are observed. In first part it was the photoelectron spectroscopy, then we had OJ electron spectroscopy, and third one was electron energy loss spectroscopy. A little modification in this, if we do, it becomes high resolution electron energy loss spectroscopy. That also helps us in analyzing the ions or material at the surface. The bombardment of sample. The sample is bombarded by high energy X-rays. It has been shown here. And then once this is done and this interacts with the matter, the target, then that loses electrons, and that ejected electron is called ejected photoelectron. The sample is bombarded with high energy X-ray of energy h nu. Each electron is held in place by the nucleus with a characteristic binding energy. X-ray photons of energy h nu collides with an electron. The energy of the photon is imparted to the electron, and if this energy is greater than the binding energy, the electron will leave the atom and carry on or carry with it excess energy in the form of kinetic energy. The binding energy of the electron can be given by the relation which is this, that is binding energy is equal to h nu minus EB or EK minus W, where EK is the kinetic energy of the emitted electron from spectrometer. W is the work function of the spectrometer induced by the analyzer, which is about 4 to 5 electron volt, a factor that corrects the electrostatic environment in which the electron is formed and measured in the spectrometer. Instrumentation. A photograph of this instrument has been shown in this slide. The functioning also has been given on the right side of the slide. ESCA mainly is made up of following components. The first is source, which gives electrons of high energy. Then we have sample holder. The third is analyzer. Finally, it is the detector that detects the outcoming electrons, and those electrons are sent to the data system which analyzes this.
Data presentation. We usually plot ESCA spectra as the count, number of electron versus electron binding energy. Using curve fitting software, we can determine the oxidation state of the sample surface by interpreting binding energy shift. The elemental composition of the sample surface can be determined by a survey spectrum, which usually includes a wide range scan from 0 electron volt to 1100 electron volt. Additionally, a high resolution spectrum can be used to discern stable peak shape and peak energy changes. These high resolution spectra usually cover a narrower energy range.
All are contained within an ultra-high vacuum enclosure. As was said earlier, one of the most important requirements for operating this system is to have high vacuum chamber. Extremely high vacuum is needed if right kind of results are to be obtained. So UHV conditions are achieved, ultra high vacuum conditions as we call it, are achieved by ion pumps or more usually diffusion pumps with cryo traps. This can be improved further by the addition of titanium sublimation pumps. Reducing pressure to as low as 10 raised to the power minus 8 to 10 to the power minus 10 torr is usually required and is achieved. It is necessary to ensure that the ejected electron does not undergo any inelastic collisions and lose energy in the process. This keeps the surface free from adsorbed gases or any other adsorbed contaminants. This talks about source, the source which gives the electron. Electrons are accelerated by high voltage. There is an X-ray tube, there is a cathode and an anode. X-ray produced when high-speed electrons hit the metal target. The X-rays are produced when the electrons from the cathode accelerate towards the metal target, that is anode, and collide with atoms and nuclei of the metal. This talks about the ionization that takes place in the atom. There are two phenomena. Primary electron beam is the one which goes in, continuous X-rays are there which hit the target, and then they produce the electrons which comes out. So we have shown here there is a nucleus, continuous X-rays are there, and primary electron beam is there which is deflected. Then we have, this is called Bremsstrahlung phenomenon. The other is K-shell emission. X-ray are produced in two ways. One which is explained just now, and second is K-shell emission. There also we have shell, L shell, then K shell, and then the lines, the X-rays are sent to the target, and then the ejected electron comes out. So this is X-ray emission, and we can depict this, which is given in the slide here. In the first one, which is Bremsstrahlung, high-speed electrons at cathode are there. Interaction with the nuclei takes place, and then the electrons obviously slow down and energy is lost. The X-rays would ultimately come out with lesser energy. Relative intensity is plotted against the wave numbers in Bremsstrahlung. Then the other K-shell emission, we find incoming electrons will be there. They knock out the electron in K-shell. Electrons of higher energy fall into K-shell, and energy lost in the form of X-rays.
ESCA used to measure elemental composition of the surface. Top 1 to 10 nanometer, usually empirical formula of pure material. Elemental that contaminate a surface. Chemical or electronic state of each element in the surface. Uniformity of elemental composition across the top surface, or lining, profiling or mapping. Uniformity of elemental composition as the function of ion beam, etching or depth profiling. Electron spectroscopy for chemical analysis, also known as X-rays photoelectron spectroscopy, is a quantitative spectroscopic technique that measures elemental composition, empirical formula, chemical state and electronic state of the elements that exist within a material. ESCA spectra are obtained by irradiating a material with the beam of X-rays while simultaneously measuring the kinetic energy and number of electrons that escape from the top 1 to 12 nanometer of the material being analyzed. XPS require ultra high vacuum condition. XPS is a surface chemical analysis technique that can be used to analyze the surface chemistry of the material in its as received state or after some treatment, for example fracturing, cutting or scraping in air, or ultra high vacuum to expose the bulk chemistry, ion beam etching to clean off some of the surface contamination, exposure to heat to study the changes due to heating, exposure to reactive gases or solution, exposure to ion beam implant, exposure to ultraviolet light. ESCA An abbreviation for electron spectroscopy for chemical analysis was introduced by Kai Segbhan and his research group. ESCA, also known as XPS, detection limit for most of the elements are in the parts per thousand range, 1000 ppm. Detection limit of parts per million are possible but require special condition, concentration at top surface or very long collection time. XPS is routinely used to analyze inorganic compounds, metal, semiconductor, polymer elements, catalysis, glasses, ceramics, paints, paper, ink, wood, plant parts, makeup, teeth, bones, medical implants, biomaterial, viscous oil, glues, ion modified material, and many others.
The various kinds of X-rays generating metals. In practice, the materials of choice are aluminum and magnesium in a twin anode configuration or simply an X-ray tube. When we take X-ray tube, the source one could be aluminum, where high energy X-rays are generated from. The values are 1486.6 electron volt. The other could be magnesium, and the energy here is 1253.6 electron volt. The design has been shown in this slide, and this is referred to as the design of twin anode. Now, the question in your mind that would be arising is, why is it that magnesium and aluminum are used? The answers are: energy of photons is high enough to eject electrons from every element of the periodic table, except of course hydrogen and helium. And that's the reason that hydrogen and helium we are not able to detect with the help of this. This magnesium and aluminum, when we use, they lead to enhanced resolution. Line widths of resultant special lines, spectral lines, inherited from line widths of X-rays, are produced. Aluminum and magnesium lines have considerably narrower line widths. Aluminum's line width will be 0.95 electron volt and magnesium will be 0.5 electron volt. The line width of the photoelectron line is maintained, obviously, and you get enhanced resolution. This has been indicated in the figure on the right side of the slide. Width of the exciting X-ray, which leads to, when it loses energy, it is further reduced, and monochromator, it passes through monochromator and transmits selected radiation to provide monochromatic X-ray radiation. There are two processes. One, small area ESCA measurements. Second, reducing analysis time. In the other second procedure, we have no satellite peaks and Bremstrong background we have, improving signal to noise ratios it will give. So we have electron gun, then monochromatation or monochromator, then we have focused X-ray beam, and it goes through the analyzer, which has been shown, and then it goes to the detector. Once it is detected and it is passed through the data analysis, the kind of spectra that we get is shown on the bottom side of this slide. So students, by now, when you have gone through this module, you would have understood the beauty of this surface analytical technique called ESCA. Now let us summarize what we have learnt here. ESCA spectra is obtained by irradiating a specimen with a beam of X-rays and measuring the kinetic energy of the number of electrons escaping out of this from the top, usually from 0 to 10 nanometer range of the surface film or from the surface of the material. The main component of a commercially available ESCA system include X-ray source, ultra-high vacuum chamber, stainless steel chamber with UHV pumps, electron collection lens, electron energy analyzer, M metallic magnetic field shielding, and electron detector system, moderate vacuum sample, and introduction chamber, sample mounts and sample stage, set of stage manipulators. ESCA detects only those electrons that have escaped from the sample into the vacuum of the instrument and reach the detector. Photo-emitted electrons can undergo various processes like inelastic collisions, recombination, extraction of the sample, recapture of the tapping in various excited states within the material. The, this causes reduction in the number of escaping photoelectrons. Once these photo-ejected electrons are in vacuum, they are collected by an electron analyzer, photomultiplier tubes, or hemispherical detectors that measures their kinetic energy. An electron energy analyzer produces an energy spectrum of intensity, number of photo-ejected electrons versus time, versus binding energy, the energy of the electrons, the energy the electrons had before they left the atom. Each characteristics energy peak on the spectrum corresponds to a specific element. The binding energy of the electron, as I said earlier, can be given by the equation given here, which is equivalent to h nu minus Ek minus W, where Ek is the kinetic energy of the emitted electron from the spectrometer. I'm sure you would have appreciated this study of ESCA. Thank you very much.